Hello all. Welcome to this interesting video session on orbit equation uh, in part number two. So, in part one, we have explained the equations in a bit detailed manner. So, the same way we'll try to explain the orbit equation in another form, which will be in terms of angular momentum and the gravitational parameter. So without wasting much time, let's get started. So here I need to construct a part of an ellipse or any conic section. Now let's say I draw a conic section like this. It can be ellipse or it can be any sort of hyperbola or parabola. So basically by default we go with ellipse only. Okay. So here now let's talk about an axis line which has been passing over here. Okay, and I define my planet body. So let's say I have a bigger mass. Let's say this is going to be my reference mass. So this is going to be a sun or it can be a very big planet. Okay. So reference to that, some other planet is going to orbit around it. So let's say we'll use a different color or something. So I'll use again green here. So this is going to be my another planet. Okay. And this planet keeps revolving maybe up to this position. Okay. Now we are more interested about the position where the planet is at the lattice rectum point. So this is a lattice rectum point, and I'll draw a line like this here. So this will corresponding to my L value because we know this is going to be my F value. Because as per Keplerian law, we already know that your sun will be placed at one of the foci, and planets will be revolving around the sun. Okay, so this is my ultimate position where it is been separated. So from here to here, it started revolving. Initially, it was here and transformed to here. Okay, now we have a motion here. Now let's say some boy is observing from this point and he is observing. Okay, this is just moving across the distance of L at sun around the foci. Okay, so this is my reference planet. The pink is my reference planet, and for the reference big body mass, and the planet it keeps revolving and it attains at a position called L, which is called the semi-lattice rectum, which we already know in a previous video. Now let us apply some the basic laws of physics here. Now let's say for any planetary motion with reference to L, we already have a centripetal force which is been given by Fc. Okay, your centripetal force which will be experienced at lattice rectum is given by at L given by Fc. We call it as Fc, F suffix c. So which is going to be equal to mv square divided by, here it is L because this is a distance of separation. Okay. Now similarly we go with the gravitational force which has been experienced. Okay, which is nothing but the weight again, but we go with the gravitational force between the two masses. Okay, the pink and the green. So we go with f of g. Fg is equal to minus gm m divided by, here it will be very careful, this distance of separation will be L square. Okay, now adding the basic forces that should yield me, so force will be conserved or force remains conserved as per the conservation of force and energy principle, or else we can go with the equilibrium principle. So force remains conserved. Okay, so in this condition your Fc plus Fg is going to yield me 0. Okay, this total system should not be unstable, it should be stable, right? So we go with Fc. So Fc is actually mv square divided by L minus of gm m divided by L square, which is going to be equal to 0. So that means your mv square divided by L is going to be gmm divided by L square. I hope this is clear. Okay, now I'll make some modifications here. We can write here mv. So you can write mv, okay, into v, okay, divided by L, which is going to be equal to gm. This is again the same. I just want to rewrite it, that's it. divided by L square. Now I want you to recapitulate the concept of angular momentum, which is given by your h. Okay, your h is given by mv into, here it is a distance L. Okay, mvl. Instead of radius, we have the semi-lattice rectangle distance, which is going to be L. So mv into L we can write. Okay, so which is fine. And if you see this equation here, L is not there. So what we do, we make some adjustment in this equation and we'll try to yield an equation like this. Into L I will multiply, and if at all I am multiplying, I will again divide here again. So L into L, okay, and that should give me again GMM divided by L square. Okay, because we are only touching in the left hand side. Okay, we are not doing anything on the right hand side. Okay, now we can regroup this term, so we can write MVL, we can write MVL into velocity term divided by the L square term, which is equal to, here I can make one adjustment. I can make Gm as simply but mu into M divided by L square, because your mu is actually called the gravitational parameters given by G times M, which is a property, or which can be a mathematical quantity for different planets or different big celestial objects. Okay, so for sun it will be having a G value and a mass value. So if you multiply it, you get the mu value of sun, and for any planet its mass and the G values remains constant. So product of G into M will give me gravitational parameter, which we have already discussed in our previous videos. Please have a look onto that. Fine. So we were telling about the adjustment thing. So we mvl into v divided by L square. So we know that mv into L at this context at the semi-lattice rectum is given by the angular momentum. So h, you don't have to get confused, is basically the angular momentum. So in a previous video we have also taken angular momentum in small h. Okay, so that you can correct. You can take even h or even small h, but you have to be uh, clear with the concept, because h is actually contains the mass. Okay, mass times velocity into the distance. Okay, perpendicular distance in fact. And we are not worried about the theta or any sort of magnitude here, because we already know, sorry, the direction here, because we already know the magnitude wise it is a product of the linear momentum. It is a rotational analog of the linear momentum. It's called the angular momentum. So if you do here the same stuff, mvl is nothing but the angular momentum h into mvl. So I write here. Okay, you can take h into v divided by L square. Even if you want to use a small h also, it's fine. But if you are using small h, and then I need to make some uh, corrections here. Okay, so I don't want to do that. So we go with hv by L square, which is going to be equal to mu into m divided by L square. Okay. Now we know the equation for the v. So here we can do some simplification. You can cancel these two gentlemen, that is L square and L square, that get cancelled. So ultimately we get hv is equal to mu times the mass of the planet, mu m, or mass of the smaller mass, mu m. So I take m this side, so I get h divided by m into v, which is equal to mu. Okay, so this h by m is called the specific angular momentum. Okay, specific angular momentum. Now in the initial stage, if at all you are taking h here, then probably you have to take your h by m to be h cap. Okay, so here I did not take any small h. Instead of taken, I have taken the big h. So you can take h here, hv, or I can take h cap or something. It's up to you. Okay, h cap v is equal to mu or something. Okay, and we already know that the v is having some term. So let's square the both sides. So let's squaring on both sides, because we don't want any complicated roots term. So v square is actually equal to, we know that as v square, the orbital speed v square is going to be equal to the mu divided by the distance of separation. So that is simply nothing but your v square is equal to mu divided by L. Okay, and if you substitute this in this equation, you are going to get h square into mu divided by L, which is equal to mu the whole square. Okay, we have done nothing here, just we have substituted the value of v square here. V square is going to be mu by L, so mu by L, if I substitute here, you get h cap square into v square is going to be equal to the mu square. Okay, so you go with h cap square, you go with the one mu get cancelled off from here and here, so you end up with h square by L, which is equal to mu. And if you take L is equal to h cap square divided by mu. Okay, so this is an important relationship that you should keep in mind, because this equation plays a very important role in case of your orbiting body. So semi-lattice rectum is a function of h square, that is angular momentum, or h cap square or something. Okay, divided by mu, which is a gravitational parameter. Now again, you can make some modification here. So L is going to be your h cap square divided by mu. So if you recall your previous work that we have done, okay, so that is R is equal to your L divided by 1 plus e cos theta, if you remember. Okay, now I can write the L value. So as we know, the L value is actually h square by mu. The same expression I can substitute over here, and I get h cap square divided by mu divided by 1 plus e cos theta, and which is a very, very important relationship in terms of angular momentum. Okay, now this is your orbit equation in terms of h, mu, and theta and e. So this plays a very important role, okay, in terms of determining the speed, determining the position vector, or in fact the position at which the planetary bodies are evolving. Okay, so at every angle of theta, at every angular momentum speed, or even this is going to be a constant, and probably we have another equation which can be yielded, because if cos theta is going to be a 90 degree, or e is going to be a zero value, then it corresponds to h is equal h square by mu, which is also equal to r, so which is basically a circular equation. So those things we'll talk in the next video. So this is how the steps are coming. So if you recall the previous equation, I'll write that also here, so it will be clear for you. So that is going to be your r is equal to a into 1 minus of e square, I believe, a into 1 minus of e square divided by 1 plus e cos theta. Okay, now if you compare the two equations, okay, you can see your h square mu is equal to the denominator term over here, a into 1 minus e square. Okay, so that is actually an additional work that we are going to do here. So h square by mu is equal to a into 1 minus of e square from the two equations. If you see here, it's quite visible. You have a denominator which is going to be equal for this denominator as well, sorry, the numerator. So the numerator value h square by mu is equal to the numerator value of a into 1 minus e square. So these two expressions are equal, and 1 plus e cos theta get cancelled off, and ultimately you end up with the equation here, because I don't want to do the simple stuff here. Okay, this is quite evident from the two equations. Now h square by mu is equal to a into 1 minus of e square, and now you go with h cap square. So you can write here h cap square. So h cap square is equal to mu times a into 1 minus of e square. So plus or minus will be coming, but go with the positive side. So you get root of mu a into 1 minus of e square, which is again an important relationship for the specific angular momentum. So that is the one additional inference that we get from this equation. Okay, so this is actually the specific angular momentum. Okay, So the denotations you do accordingly because this is convenient for me, and that is the reason I have taken h cap here. So if at all you are going with small h for angular momentum, you can take the small h, and h by m you can take for h cap or h star or something. So up to you. So here I am bit okay with taking h cap, so I have taken h cap. So if you want to take the angular momentum a big h and a specific angular momentum a small h, that also it's quite welcome that you can take accordingly. So ultimately the concept remains the same. Whether you take a small h, h cap or big h, it's all the same. The concept remains the same. So I think this concept is helpful for you. And this is an equation in terms of mu a into 1 minus of e square, which is nothing but the eccentricity value. Okay. Again, if you substitute as 0 here, this is going to yield a circular equation, which is going to be h cap square is equal to root of. So here there won't be square. Okay, you get only h cap. Okay, so h cap is equal to root of mu a into 1 minus of e square. So this is the equation that we have. We need to focus. Okay, so your h is equal to root of mu a into 1 minus of e square, which is the specific angular momentum equation. And this should not be get confused, okay? I hope this video is clear for you, and this session will be much more taken to the next level in our preceding videos. So please try to practice and try to obtain some good insights. And wherever you feel like some doubts are coming, please let me know in the comment box so that I can rework and redo it again for your understanding. So we'll wind up here. So we'll see you in the next video then. Thank you so much.